Now we will discuss about drift of electrons and the origin of the resistivity. Now, in the absence of any electric field applied on the charge carriers, so they don't have a resultant mobility or a resultant velocity in any given direction because of thermal agitation. Due to heat energy, the free electrons in a conductor will be moving randomly in different directions. So when they are moving means they move and collide with the ions of the solid or with the atoms, and hence their directions will be changing. So they will have random motion. Therefore, in the absence of any electric field applied on the electrons in the conductor, their average speed will be 0. Suppose if this is the speed of an electron, and if you sum up the velocities of all the electrons in a conductor due to thermal energy and divide with the number, then you will get this value is 0. So they don't have a resultant velocity in any direction. Hence there is no current in a conductor even though there are free electrons. Suppose if you apply an electric field by connecting a cell or a battery to the conductor and creating a potential difference across the ends. So let us suppose this is a conductor. Say some cross section A. Let this cross section A. Now an electric field is applied by connecting a source that maintains a constant potential difference. As a result, what happens? The electrons will get accelerated in the opposite direction of the electric field. So there will be a flow of charge carriers from right side to left side. And when they move, what happens means they will be colliding with the lattice ions even now also, but they get again accelerated because of the field applies a force on them. Hence the charges will experience a force, and hence even though their speed decreases or velocity decreases in a collision process, again the velocity increases. Like that the electrons, they move, collide with the lattice ions or the atoms, their velocity decreases, and they get again they acquire velocity in a given direction. So like this they move as if a plow moves in a field. This type of movement of electrons in a conductor is called as drift speed. So that is called a drift speed or drift velocity. So they move with some resistance for their motion. So such type of velocity is called as drift velocity. And now let us derive a formula for the drift velocity. Using this equation, that is the velocity of a body at any time instant of time is given by initial velocity plus acceleration multiplied with the time. This is a relation which you know already. So using that, the velocity of an electron at any instant of time is given by the initial velocity plus acceleration is given by actually minus dE by. So you know that this is the acceleration because this is the electric force on the electron and m is the mass of the electron. So therefore we can write like this: minus the acceleration into the time you are considering. Now let us calculate the average velocity after a certain time after the collision. Let us suppose after first collision and before going for the second collision, during that interval of time. So after that time interval, what will be the final velocity of the electrons? So we calculate the average final velocity of electrons after a collision. So that is nothing but such average velocity, we call it as drift velocity. So we write like this: the drift velocity. So after the average velocity during successive collisions of the electrons is given by We know this is also enough to take average initial velocity minus E by A. Here we take this time as the average time between successive collisions. So that average time between successive collisions is taken as tau. We call that tau is nothing but relaxation time. Relaxation time. So time interval between successive collisions of the electrons passing in the conductor. So why we take that is also average value means all electrons will not take the same time for successive collision. So the time interval between two collisions of all the electrons need not be same. Hence we take the average of that. So let us call that as relaxation time tau. Now here, see, this is mass. This is mass. Now, therefore, the average velocity initially is 0, as I already explained here. So, therefore, drift velocity is given by the acceleration of the electrons multiplied with the relaxation time or time interval tau. Now, we know through any cross section, the charge that crosses in the direction of the electric field, so that is the positive charge. Because if you say some q amount of negative charge crosses from right to left, an equivalent of positive charge crosses from left to right. So in that way we may consider. Therefore, keeping that in view, so the charge that has crossed during a time interval is given by I into delta t. So let us suppose the charge carriers move from one end of the conductor to the other end. So in such case, this distance will be considered the average drift, that is average velocity, drift speed into the time interval must be the length of the conductor. So let us assume that in the charge carriers take this much of time to move from one end to the other end of the conductor. Hence, this can be written as velocity into time gives the distance. Hence, this distance is the length of the conductor. Now, and charge can also be calculated like this. Delta Q is equal to, let us suppose you have n number of electrons per unit volume, and E minus E is the charge, and then over the volume of this much. So volume is given by length in the area of cross section. So that is Vd into, so delta T into this area of cross section. So number of electrons and the volume of this conductor. So you are multiplying with the charge. So this entire quantity gives a total charge that is passing from right side to left side. Hence I can write the positive charge that is crossing the conductor can be taken as N into E into Vd delta T into A. So in that way we can calculate the total charge. Or we can take the volume multiplied with N, then we can multiply with E. So that is, this is the volume term. This is the volume term multiplied with N. You will get total number of charge carriers. Each charge carrier has a charge of E. So therefore, volume multiplied with N and the charge, that gives the total charge crossing the conductor. Since y we have taken opposite to the direction of the electrons, we are using this plus sign. So we drop the negative sign here. Now, therefore, I can equate these two. So this one. I will equate these two equations. Then I can write like this: I into delta T is equal to N into E into Vd into delta T into A. So this delta T gets cancelled, and I can write I by A is equal to N E BD. But we already derived the formula for the drift speed. So the drift speed is given by this equation. So you can draw this negative sign, and hence you can write the magnitude of this. This is equal to NE, that is E capital E by M into tau, relaxation time. So therefore this is equal to NE square electric field strength by mass of the electron into tau, and this I by A is called as J. That is, already told you, this is the current density term. So this magnitude, if you put a bar, then this is the magnitude of the current density. And in vector form, you can simply write J bar is equal to N E square by M into tau into E bar. So this is equivalent to sigma E bar. So we arrive at a formula for J bar and E bar. See, this is what I earlier told you while discussing the Ohm's law. So we arrive at the Ohm's law by starting with simple electrical conduction. So we started to the electrical conduction taking place in a conductor, and finally we arrived at this law. This is nothing but equivalent to Ohm's law. Okay, so the resistance or resistivity of materials is due to the mobility of the charge carriers, because the charge carriers undergo collisions with the lattice ions or atoms, and hence they lose their energy, their speed decreases, and again they get accelerated by the action of the electric field, and then they again acquire velocity and they move. So like this they go on moving from one end of the conductor to the other end. So this is the cause of resistivity of conductors, and in this way we can explain what is the origin of electrical resistivity. Then we talk about another important term, that is mobility. Mobility. See, mobility means the freedom with which the charge carriers can move. So in solid conductors, electrons are the charge carriers. So the mobility is defined as the drift velocity per unit electric field strength. So this is called as mobility. So drift velocity of electrons per electric field strength is called as drift speed, or called as mobility. So we have shown that already. This is this magnitude of this is small e capital E by M into relaxation time by electric field strength. So this electric field strength gets cancelled, E by M into tau. So that is the formula for mobility of charge carriers. So from this we can write the unit also. So that is velocity meters per second. You know, Newton per coulomb is this, or volt per meter. So therefore we can write meter coulomb per Newton second. So you can write like this also, or volt per meter. So in terms of volt per meter also you can express the formula for mobility. That is, if you write that in terms of meters per second by volt per meter, so then this goes to numerator, that is meter square volt second. So that is the limit of mobility. Then we will talk about limitations of Ohm's law. And Ohm's law is not a universal law. It is only a relation that can be used for calculating the voltage or current if the resistance is known. So it can be used as a mathematical relation, but it is not a universal law. So let us discuss about limitations of Ohm's law. Limitations of Ohm's law. See, Ohm's law simply says that V is proportional to I. So, one must expect a straight line if a graph is drawn between voltage and current for any conductor. One must expect a straight line, but it is not always a straight line. So, taking the voltage and current on the y-axis and x-axis, if you draw, in the case of a good conductor, so you may get a straight line. And at large voltages, the curve it will become curved, so that linear relation is lost. So this is one limitation. Even for a good conductor, at high voltages, the voltage current relation is not linear, so that linearity will be lost. That is practically observed. The second one is there are some materials for which if you keeping the voltage constant, if you reverse the direction of the voltage, the magnitude of current changes. You don't get the same current value, you will get a different value. So for example, as in the case of a junction diode, or in case of a semiconductor diode, you are going to study it in the later chapter, that when in the forward direction, if the voltage is increased, the current increases exponentially, and that is in the order of milliamperes. And reversing the voltage, so in the reverse direction, if you increase the voltage, the current increases, but in microamperes. In microamperes. So the current voltage characteristic doesn't hold good in the case of semiconductors. So that is diodes or transistors. For them, in forward bias, that is when the voltage is increased in the positive direction, current increases exponentially. But whereas in the reverse direction, if you increase the voltage, almost the current through the semiconductor won't increase that much, very slightly increases, and suddenly there will be a surge of current. But that increase also in microamperes. So in that way, the semiconductors, diodes and transistors, vacuum tubes, they disobey Ohm's law. And another thing is, there are some materials like gallium arsenide. Such materials should have the same current value for different voltages. So this is somewhat peculiar. So taking voltage on x-axis and current on y-axis, if you draw a graph, you will be getting a curve like this. This shows that for the same current value, you have different voltage values. So such materials are used as thermistors. So for such type of compounds, the linear relation doesn't hold good. So like that, there are some materials for which Ohm's law is not applicable. So we can say that it is not a universal law, it is only a mathematical relation. But those materials which obey Ohm's law are known as ohmic materials. So all metals can be treated as ohmic materials. And some materials such as semiconductors, resistors, that is diodes and transistors made of semiconductor materials, vacuum tubes, are examples for non-ohmic materials. They are known as non-ohmic. So they are called as non-ohmic materials. So these are the limitations of Ohm's law. Okay. So we will next discuss about the temperature, about the types of resistors, the temperature dependence of resistor, the power dissipated in a resistor due to flow of current. All such topics we will discuss in our next class.